Next up is the limit comparison test. So this is a good test if like the direct comparison test doesn't work and and also for like really messy looking algebraic functions. So let's take a look at this example. The sum of 1 over 2 plus the square root of n. I would compare that to 1 over the square root of n because that would be a p-series to the 1/2 power. And I notice that because p is equal to 1/2 and that's less than or equal to 1 but greater than 0, the series diverges. Okay, but remember using the direct comparison test, oh yeah, and then, well, let's go over here. 1 over the square root of n versus 1 over 2 plus the square root of n is the denominator of the right ratio is larger, so that means that it's actually smaller than a smaller ratio than the one on the left. So we have a sub n and b sub n. So a sub n is the smaller and b sub n is the larger. Okay, we know that b sub n diverges, but that doesn't tell me anything about a sub n. So the direct comparison test won't work here. So we're going to use a different test called the limit comparison test. So basically we're going to compare our series to another series that basically has the same rate of change or a very similar rate of change. Okay, so we can kind of generalize what is happening with the series. So the things that we need: a sub n has to be positive, b sub n has to be positive, and then we need to take the limit as n approaches infinity of the ratio of a sub n to b sub n. And it has to equal a finite number. Basically what we're testing is if the ratio that we are comparing, if they are decreasing at a similar rate. So if they have a similar rate of change, because what you end up with is like an eats DC situation. Okay. So if the limit is finite and positive, then either both series converge or they both diverge. Okay. So here we go. Really what we're going to look for is to make this messy function into a p-series. Okay, because p-series, I can figure out if it converges or diverges really quick. Okay, so what we're going to do is take basically the leading terms of each ratio here. Okay, and oops, these are my wrong notes. Here. And we're going to just take the highest power of n and the numerator and the denominator. We're even going to take away the coefficient. So like for this one, I would compare to 1 over n squared. The next, I would compare to 1 over the square root of n. I'm just going to take the highest term and take away the coefficient and everything, just leave me my variable. So this one I would take n squared over the square root of n, which you could simplify if you want. Okay, n squared over n to the 1/2. Subtract the powers to give me n to the 3/2. Okay, this one I would compare to 1 over 2 to the n. This one is not a p-series, it's a geometric series, but we can also figure those out. Okay, all right. We're going to determine the convergence or divergence of each series. So we have the sum from n equals 1 to infinity of the square root of n over n squared plus 1. So first off, we need to compare to the square root of n over n squared. and I am just going to go ahead and set this up as the limit as n approaches infinity of a sub n over b sub n. So a sub n is the square root of n over n squared plus 1 all over b sub n, which is this, okay, over n squared, multiplied by the reciprocal. Those cancel. It's n squared over the square root of n. I get the limit as n approaches, looks like my n squared, the square root of n's cancel, as n approaches infinity, of n squared over n squared plus 1. Whew. Okay, so this is a eats DC situation. The degree of the numerator is the same as the denominator, so we divide the coefficients to give me, we are approaching 1, the value of 1. 1 is, which is positive and finite. It's important, okay? 1 is positive and finite. So we know that either, you don't have to write this part, but either both series converge or diverge. So they both converge or they both diverge. So now, since we set up this nice little series here, I'm going to set it up as the sum from n equals 1 to infinity of the square root of n over n squared. And that's going to give me the square root of n is equal to 1. This is n to the 1/2 power, so I get 1 over n to the 3/2 power. And I can see that this is a p series. So p is equal to 3 over 2, which is greater than 1. So I know that the series converges. So since our comparing series, n is equal to 1 to infinity of the square root of n over n squared, converges by p series, then the sum from n equals 1 to infinity of the square root of n over n squared plus 1 also converges by limit comparison test. Okay, next one. We have the sum from n equals 1 to infinity of n times n squared, 2 to the n over 4n cubed plus 1. So I'm going to compare to n times 2 to the n over n cubed. Remember, I get to drop the coefficients, but I do need that base of 2 since it's 2 squared, okay? I can simplify this to 2 to the n over n squared, since those will cancel. All right, so let's go ahead and set up our limit and make sure that our a sub n rule and our b sub n rule are growing at a very similar rate, okay, very close rate. So as n approaches infinity of our original, which is n times 2 to the n over 4n cubed plus 1 all over 2 to the n over n squared, multiplied by the reciprocal. Okay, and I see that the n 2 to the n will cancel, and that leaves me with the limit as n approaches infinity of n times n squared is n cubed over 4n cubed plus 1. Look, eats DC. So I divide the coefficients to give me 1/4. 1/4 is finite and positive. Okay, so from there, we can go ahead, because the because the limit as n approaches infinity of a sub n over b sub n is finite and positive, then we can go ahead and evaluate to see how the sum of b sub n, if it converges or not. So I'm going to do b sub n would be 2 to the n over n squared. And I'm just going to set this up as the limit as n approaches infinity to see what happens of 2 to the infinity, 2 to the n over n squared. And I notice that as the numerator is going to grow a ton faster than the denominator, so an exponential versus a quadratic, right? What we get is 2 to the infinity over infinity squared. This is Bobo. No, sorry, it's Botan. So as n goes to infinity, the function will also go towards infinity, which does not equal 0. So the series 2, the sum from n equals 1 to infinity of 2 to the n over n squared diverges by the nth term test. We haven't seen that one in a while. Okay. The nth term test. Okay, and therefore the series n, the sum from n equals 1 to infinity of a sub n, which was n times 2 to the n over 4n cubed plus 1, it also diverges. But we have to say it's because we compared it to this other one, so it diverges by the limit comparison test. Okay, next up, last one. So we have the sum from n equals 2 to infinity of 1 over the cube root of n squared minus 2. Okay. And this is pretty nasty looking. I'm going to go ahead and just try and compare it to something that has a similar setup. So 1 over the cube root of n squared. Okay. So let's take the limit as n approaches infinity of a sub n, which is 1 over the cube root of n squared minus 2, all over b sub n, which is 1 over the cube root of n squared. Okay, reciprocal time. So multiply by the cube root of n squared. So I get the limit as n approaches infinity of the cube root of n squared over the cube root of n squared minus 2. Okay, look, these are growing at the same rate, pretty much. Pretty close, pretty close. So this is a each DC situation. So we divide the coefficients to give me 1. 1 is finite and positive. So both series either diverge or converge. So we now need to test that. So we're going to test the easier series, this one, okay, as n equals 1, the sum from n equals 1 to infinity of 1 over the cube root of n squared. I can write that as something nicer looking. The sum as from n equals 1 to infinity of 1 over n to the 2/3. I'm like, oh, it's a p series. Okay, so p is equal to 2/3, which is less than or equal to 1, but greater than 0. So this series diverges. Okay, and we just need to name everything now. So the series n equals 1 to infinity diverges by p series Therefore, the sum from n equals 1, from 2 to infinity, also diverges by the limit comparison test. Okay, those are your comparison tests.